All right, good morning, everyone, and welcome to the last Friday of the semester. Well, I guess there's still finals, but the last Friday class that we're going to have. So as I'm checking everyone in, something to watch out for. Um, I'm going to be putting up sometime today um, an outline of what to expect for the rest of the semester. Um, so we only have a few more lectures, a Tuesday lab, and a couple assignments in there. So I'll try to lay out what's everything that's going to happen so you can start putting together your final exam schedule. Um, the big thing to know is our final exam. Is going to be, well, I guess there are two things. Today, your third exam is going to be posted this afternoon. So watch out for that. That is due the last day of class. And the final exam is going to be posted that last day of class and due on Monday, the day that our final exam was originally scheduled for. So there will be a lot of math happening, but it's all kind of spread out. So hopefully that'll give you time to look up all of these tests that we're looking at and fit it into the rest of your final schedule. Okay. So let's talk about where we were last time. So let's do here. That's too close. So what we introduced last time was this idea of what's called a power series. And a power series is a series with a variable in it where the question isn't, does this converge or diverge, but rather, for which x does it converge? Sorry. Hold on just a sec. Okay, great. So we have a series, and we say that a power series is centered at A if the if we have x minus a, and that's raised to the nth power. So we'll have some coefficient which depends on n. This could be constant or could have any other quantity in n. But a power series has this very specific form where the variable, the place where you can have different x's and then get different numerical series for those x's, it has to look like x minus a to the n. What happens, and so there's a, well, first there's a special case where if you let this n be 0, you would just have cn, or you let a be 0, you have cn times x to the n. And if you have a series centered at 0, looks like, I'll just use some letters. There's some const, no, I don't want to use A. So there's C0 plus C1 times X plus C2 times X squared plus C3 times X cubed, and then so on. So the idea behind power series is that a power series is like an infinite polynomial where the coefficients can change depending on which one you're looking at. So Cn means that exactly what number goes here can depend on which coefficient you're looking at. But if you were to actually write them all out, you would get an infinite polynomial. And part of what makes power series really nice, we'll see a lot of things which can make them nice mathematical objects, is that the question, when do they converge? There aren't a lot of different answers to that question. So the options are either it only converges at A, and in that case, if you put in A, every x minus a to the n is 0, so you only get whatever your constant term is. One option is that it converges for every x. The intermediate case, which has the most going on, is that there's some number r called the radius of convergence. And what this means is that there's some point, so if you have your center A, and this is kind of the reason why it's called the center, is that there's some point where if you go r units in either direction, you converge inside this interval, and you diverge if you're outside it. So there's this cutoff point where if you're in here, the absolute value of x minus a is less than r, so you are closer than r to the point A, or you're within r units of a is the kind of distance reading of this absolute value inequality. So if you're within r units of a, you're going to converge. If you are more than r units away, you're going to diverge. A small wrinkle is that you have these endpoints when you're exactly r units away from the center. Those can go either way. You could both converge or diverge of one of each. And the actual interval you get. So r is the radius. That's how far out you go to get the endpoints of these intervals. The interval of convergence is the set. So it's everything between these points and include the endpoints if the series converges at those points. And so we have the interval of convergence, which is the actual set of points. The radius of convergence is the r here, or infinity in case 2, if we think of the whole number line as an infinite interval, or 0 in the case of just the center. We think of a point as an interval without any length. So as an example, we can say here is a power series centered at -1, because in this case, the Cn is 1/4 to the n plus 1. So the part that the coefficient that just has n in it, that's this Cn. That's the coefficient, and it changes depending on which term you're looking at. The x plus 1 to the n, that's what makes it a power series. And the formula for power series is x minus something. Here, because we're adding, we're really subtracting a negative, and that -1 is the center. So in deciding when this converges, you can pick specific x's and put them in, but we want to be more systematic about that. And one way to do it is we can apply the ratio test or the root test. We did the root test here, but the ratio test will get you to a similar kind of endpoint, and then you'd proceed in the same way. So if you apply the root test to this, the first thing is you take the absolute value, which just makes it show up on this x plus 1 raised to the n. If you take the nth root of this, then it cancels with this nth power on the absolute value of x plus 1. It cancels with this nth power on this 4. And after breaking 4 to the n plus 1 into 4 to the n times an extra factor of 4, we get the nth root of 4 here. And as a fact, we can just take as the way that this works. You could check it with I think L'Hopital's rule, or you could check this explicitly, but the limit of the nth root of a fixed number is 1. So when we take the limit, the only thing that happens is we take the nth root of this of 4, see what happens to that. That goes to 1, and that means that the limit that comes out of the root test is the absolute value of x plus 1 over 4. And then we have to think, what is the root test saying? It says the series you started with converges if, when you take the limit, that is less than 1. So that's where we get this inequality. The inequality that tells us which x's make this converge are the x's which satisfy this inequality. As a first step, we can multiply both sides by 4 to get the absolute value of x plus 4. And we can keep solving this, but right here, what we see is that we can tell what the radius of convergence is. So if we go back to this first slide here, part 3 says if there's a number r, so you converge if you're closer, if you satisfy this inequality, and diverge if you satisfy the flipped inequality. That's exactly what's happening here. If this inequality is true, that means this limit is 1. Sorry, this limit is less than 1, which means the root test said you converge. If you have the flipped inequality, that means this expression is greater than 1, and the root test you diverge, says you diverge there. So at this point, this is where we can read off the radius. If we keep solving the inequality, we can get the actual endpoints of the interval. So absolute value inequalities means the x plus 1 inside is less than 4 and greater than negative 4. If we subtract 1 from both sides, we get negative 5 and 3. So what we know at this point is the interval of convergence is something like negative 5 to 3. But we have to decide about the endpoints. If we use either closed brackets or open brackets, or a mix of them. So we know that the interval is going to look like this for some choice of brackets, but depending on what happens with the endpoints, we have to check those on their own. And this matches what we know coming from the radius, because from the radius, what we can say is that the center was negative 1. That's from the form here, x plus 1 says where center is negative 1. If the radius is 4, we can go 4 in either direction and still converge. But if you start at -1 and you go down 4, you get this -5. And if you start at -1 and you go up 4, you get to this 3. So that's the way in which all of these different ideas hang together. The radius is how far you can go out from the center, which is what you get by solving the absolute value inequality. But what we need to check is that, what do we do with these endpoints? And with the endpoints, we really need to put them in, see that we get an actual number series, and see what that series does. So if we put in -5, remember we're putting it into x plus 1 to the n over 4n plus 1. If we put -5 in, then we get -4 raised to the n. We can break that apart into the -1 to the n and 4 to the n. We get some cancellation, and this series diverges. Here, this is geometric with r equals -1. And in that case, this series diverges. If we put in 3 into x plus 1 to the n, we get 4 to the n. But then we get some cancellation too, giving us a 4th. And this, we can say, the terms of this are constant, so it's the limit of the terms is a 4th. And because that's not 0, this series diverges by the test for divergence. So what this means is that the endpoints, neither of them actually works. If we put either endpoint in, you get a divergent series. So the interval is only -5 to 3. And we knew it would be at least that, but the question is, do we add on either of the endpoints? Questions about this problem? Of how we find these intervals and radii of convergence. In this case, there is another way we could have done this, which would help us by not needing to do these endpoints here. So another way of looking at this series, the root test definitely works, the ratio test also works. And also, if you notice, this is geometric. And it looks like 1/4. So if we take this 4 out, we have an extra 1/4. And then inside we have x plus 1 divided by 4 all raised to the n. So if we take this extra 4 out, then we have x plus 1 to the n divided by 4 to the n. We can write that with a single exponent. And that jump gets us to right here. A geometric series converges if the absolute value of what you're raising to the nth power is less than 1. And that's exactly what this inequality says. But even further, we know that geometric series never converge when r equals 1. So r equals 1 would correspond to the endpoint. So that's where the -5 and 3 actually come from. So if you look at this as a geometric series, you know that it converges, that it diverges at the endpoints, but those, because that corresponds to having 1 to the n or minus 1 to the n, which we know diverges. And in fact, clear this out. That's what we saw. If you put in 3 and -5, you get -1 to the n, or in this case, it's just not written that way. You have 1 to the n. So the endpoint cases turn out to be geometric with r equals 1. And if you notice you're dealing really with a geometric series from the beginning, you can say, because it's geometric, I know the endpoints diverge. I don't even have to check them. But if you don't, or if your series isn't geometric, or if you approach it by the ratio test or root test, you really do need to check the endpoints. So power series are the object of interest. It uses all of the sequence and series stuff we've been talking about before, but the big reason why we care about them is the next section, which is, or kind of the next topic. This doesn't match our textbook. This is from another book that I used. But the idea of representing functions as power series. And here's an example which shows what I mean by that. So here's a power series. Because it's just x to the n, it has center of 0. Because it doesn't have anything else, all the coefficients are 1 in this case. So it's just these powers of x all added up. This is geometric, and we can check that it converges if it has absolute value, if x has absolute value less than 1. So because this is geometric, it converges for x in this range, and so we'll write this out. So we know these two things since converges if absolute value of x is less than 1. So that's the fact that really says this 1 is where the radius comes from. And if you write this out as an interval, this is the set that you get. So this is a power series, and we can tell the interval on which it converges. But we can also say this is geometric. And if it converges, we know what it converges to, because there's a formula for geometric series, for the sum of a geometric series. And the sum of a geometric series, if you pick an x, is 1 over 1 minus r, where the r is the x, is where the variable goes. So that's what we subtract down here. So we know this is a power series. It converges for these x's, and if it converges, this is what it converges to. Another way to put this is, if you look at, or to put this in an equation, if you look at x's whose absolute value is less than 1, this series equals this function. So what this is saying is that this series represents a function, and the value of the function at a particular x is 1 over 1 minus x. So this, maybe this seems like hyperbola, but this is perhaps one of the most important facts, certainly from the sequence and series part of the course, maybe in all of Calc 2. But the idea is that a power series defines a function on its interval of convergence. So if you think about the interval of convergence as the domain, these are the x's for which you can plug them in and you get something that makes sense, meaning those are the because those are the x's for which it converges, for which you get a number out. And so what we're saying is that this is a function, this is another function, and these two functions do the same thing. So this sum from 0 to infinity of x to the n is what we'll call a power series representation of 1 over 1 minus x. Okay. Because if you pick an x and put it into this series, if it's in this range, that's going to converge, and the number you get will be equal to if you just put x into here and did 1 over 1 minus whatever x you got. So this function has a power series representation, the series x to the n. There's another way of looking at this, which explains why this is, why I said this is actually important. So 1 over 1 minus x, we're saying that's equal to this series. And this series, if you actually write it out, is 1 plus x squared plus x cubed plus so on. So this infinite polynomial, if you evaluate it at an x in this range, will give you 1 over 1 minus x. But how we understand series is that the series is the limit of partial sums. So in this case, the partial sums are these partial polynomials. And if we look at the graph, we see something really interesting. So let me get to this one. Here we go. Okay. So here is 1 over 1 minus x. It has an asymptote at 1, right there. If we start looking at the partial sums of that series, so the series representation of 1 over x, we said this was equal to 1 plus x squared plus x cubed plus so on. If we start looking at those, so y equals 1 is not actually that good. 1 plus x is all right. This, if you, so you can check this, 1 plus x is the tangent line to the function at x equals 0. So if you took the derivative of this and found the equation of the tangent line at 0, 1 plus x is what you would get. But what happens is that if we keep having more and more of these terms, so 1 plus x squared, this parabola, is even closer to the red 1 over 1 minus x than the line was. This green cubic, 1 plus x squared plus x cubed, is even closer. If we zoom in some, what we can see is that the green line here stays with the red line a little bit longer than the parabola did. And here the green line is staying with the red line a little longer than the parabola did over here. And if we keep going, this purple quartic stays with the red line even longer. And if we make a big jump to x to the, how many do I have? X to the 8, this black line stays with the red original function even longer. So up here, the black line is staying with the red line for quite a while. It eventually is getting some separation, but it's still pretty good. So what we're seeing is that if you have a function with a power series representation, if you look at the partial sums of a series are polynomials. And those polynomials, in a sense, converge to the function that you started with. As you go further and further out in the polynomials, as your polynomials get longer and longer, your polynomials more closely approximate the original function. And what we notice is it's getting really good as long as you're between -1 and 1. A problem is that, well, it's not perfect because at 1, the original function has an asymptote and none of the polynomials do. So it doesn't work at 1, but it gets better as you have more terms. Over here, all of the, at -1, every polynomial, and if we, well, for the polynomials, we can see at -1, they're always 1 or always 0. So they're not close to the original function here, which is a half. But we get closer and closer, or we lay down more and more of that function before we turn away and go to 1 and -1. So this is part of the power of having a power series representation. If you have this, you can say, rather than computing, or if I want to approximate this function, I can pick a polynomial with a ton of terms formed in this way and use that. And for x's close to 0, I'll be pretty good. So a few things in there. One fact from calculus is the tangent line is a very good approximation of the function close to the tangent point. So this tangent line 1 plus x, if you're really close to 0, the tangent line is really good. It gets worse as you go away, but close to that point, the tangent line is a good approximation. The same thing happens with these longer partial sums of a power series. Close to the center of the point of your series, the approximation is really, really good. As you get further away, it gets worse. But if you're close to the center, well, at the center, it's exactly correct. Close to the center, it's pretty good. So one thing is that if you have a power series representation, you can get a very good approximation close to the center. What's also good is that polynomials are easy to compute. Powers of x, maybe with coefficients, those are pretty easy to put in a calculator. In this case, 1 over 1 minus x, that's also not hard. But imagine if you had sine or something. If you had a power series for sine, then you can say, I want to know sine of 4. I can approximate that by picking a large enough polynomial. And you might say, well, why don't you just use a calculator? And I would say, how do you think calculators approximate things? One way is you have a function, pick a large enough polynomial that it really closely approximates your function. Um, and use the polynomial, and the answer you get will be close enough. So functions can be represented by power series, and there are a lot of reasons why that's a really beneficial and interesting representation to have. So we'll talk about, so we're not done with class yet, but what we can talk about is what functions can be represented as power series, and how can we find those representations? And the first way that we'll start with is, here is one function we know has a power series representation, because this is essentially the sum of the geometric series formula. If you have just x to the n, as long as it's in this range, it converges, and it converges to 1 over 1 minus x. So this is a function who we know has a power series representation. And one way to proceed is to exploit this to talk about power series or get power series for other functions which are kind of similar to this. So what I mean by that, here using, so this is the series expansion that we're starting with. Series expansion or series representation, those are synonyms that I'll use kind of interchangeably. But a question is, what if we have this function, 1 over 1 minus 2x? And the way we can look at it is say, well, this function is basically the same as this function, except that this has an x and this has a 2x. And when we have this series expansion, this thing here, this x, is what was raised to the power. So make the same move with this series. Take this form, but instead of x being raised to a power, 2x is what's raised to the power. So that is what's happening here. We have the right form. It's basically this 1 over 1 minus something, but that something is now what we raise to the power. So if you notice that your function is 1 over 1 minus something, we can find a series representation for that by taking the something, and that is what's raised to the power. So 2x is our something, so 2x is what's raised to the power, and we can write that, if we break it apart, this is the kind of standard way that power series are represented. There's the x to the n, and then there's the coefficient part. And so we know that because of how we obtained this, we know that this series converges if the r is less than 1. But now, rather than r being x, as in our original series, our r is 2x. So we know that this series converges and converges to this function if 2x has absolute value less than 1. And given this, we can solve this inequality. You can factor the 2 out of the absolute value and then divide both sides by a half. And that gives us our inequality telling us where this converges. So in this case, we can say the radius is this 1/2, because we need it as the absolute value of x plus or minus something. And only after dividing by 2 do we get it in that form. And so the 1/2 is the radius, and the interval is -1/2 to +1/2. And because it is geometric, we know that the endpoints aren't going to work. If you put a half or -1/2 into this expression, you'll get 1 to the n or -1 to the n, and both of those diverge. Before we see anything else, questions about why this is the series for 1/1 minus 2x, and or why we know these are the radius and interval of convergence. Okay. So this general strategy is if you know a series for a function, then if you change that function, you can make the corresponding change in this series. The change being change the variable to something else. So we can make the same thing if we look at 1/1 plus x squared. So this, what we want to do is say that we want to rewrite this 1/1 plus x squared so it looks like 1/1 minus something. And that something is what's going to be raised to the nth power. And we can do that by saying, well, addition is subtracting, or that is subtracting a negative x squared. And this is the form that we want, 1/1 minus something. So that function can be represented by the series where negative x squared, that's what's being raised to the nth power. And what we can write here, how we can rewrite this, is to see what this looks like as a power series, which means we need to have the coefficients, which we can take this negative, make that -1 to the n, and then the power part, x to the 2n. Now this is kind of different because so far all of our power series had the exponent being n, but now we have 2n. What that means is that we only are going to get even exponents. So if you try writing this out as what is the infinite polynomial version of this? If you put in 0, -1 to the 0 is 0, 2 to x to the 0 is 0, sorry, not 0, -1 to the 0 is 1, x to the 0 is 1, so the first term is 1. If you put in 1, you get a negative from this, and then x squared. If you put in 2, you get 1, and then x to the 4th, positive x4. And so negative x to the 6th, positive x to the 8th, negative x to the 10th. So this is also a power series. Power series don't have to have every power represented, because what's happening is all of the way that we understand what's going on is it's a polynomial, but all the odd coefficients happen to be 0. So when you're using polynomials, you don't always have every single power from the constant term up to whatever your biggest power is. Sometimes you leave out terms, and with the understanding that sometimes coefficients can be 0, and so not every power is represented. And that's what's happening here. From the 2n, we can see when we put in specific n's, we're only getting the even powers. What we also want to think about is where does this converge? And the convergence is that geometric series, they converge exactly when whatever your R is, whatever is being raised to the nth power, when that has absolute value less than 1. And so in trying to identify this, we can get rid of the negative. And instead of taking the absolute value of x squared, we can take the absolute value of x and square it. And if the absolute value of x is less than 1, then the absolute value of x also has to be less than 1. If you take the square root of both sides, it keeps the inequality going in the same direction. So the absolute value of x is less than 1. Which means that we have radius 1 and the interval is -1 to 1. Questions about this problem or any of this kind of representing functions as series? So we'll see another way, but a big way is if you know a series for a function and you substitute something in for the variable in that function, you can make the same substitution into the series, as long as you end up with a power series. As a last example for the day, let's say x over 4 minus x. So first, forget about the x on top for a second. We'll just look at 1 over 4 minus x. This almost has the right form, but there's a 4 here. In order to really use the geometric series formula, we need it, though, to be 1 minus something on the bottom. And so if we want this to be a 1, we can factor a 4 out of both of these terms, giving us a 1 there. But then because this x doesn't have any 4s, we have to divide by a 4. So we have this series, or this function, and we know that 1 over 1 minus something, that is a geometric series where you raise this something, x over 4 in this case, to the nth power. And since this has a 1/4, we multiply that in there also. You can have it outside or inside, either place works. So rewriting this, we can raise each of these parts of the fraction to the nth power, combine the 4s, and we get that this is the series, x to the n over 4 to the n plus 1. To check where this converges, though, this first form is really what we want, because now we're thinking we have a geometric series. This converges if the r in here is less than 1, has absolute value less than 1. We can break the absolute value up over the fraction and multiply both sides by 4. And right here, this is where we figure out the radius. Here, the radius is 4, because the radius shows up when you have the absolute value of x, or x plus or minus something, less than some number. If that's the form of the inequality that tells you when it converges, that something is what the radius is. So we can say that if you had a 1 on top, 1 over 4 minus x is represented by this series, x to the n over 4n plus 1, and it converges between 4 and -4. Why we did this ahead of time is that if you have an extra factor, an extra x, we can say break it apart, find the series from 1 over 4 minus x, and then distribute that x through. Here, we're thinking multiply every single term by an extra factor of x, which means add 1 to every power of x. You can really think of adding the exponents together, the 1 for the x times the n for x to the n. And so this function is represented by the series for n equals 0 to infinity of x to the n plus 1 over 4n plus 1, which means if you write this out, what these look like, this is a fourth plus x over 16 plus x squared over 64. So the powers of 2 keep increasing, or the powers of 4 increase on the bottom. We have 1 extra x on the top each time. The difference is, if you start with this bottom series, is that every term has an extra x. If you put in 0, you get x over 4. If you put in 1, you get x squared over 16. Put in x equals 2, you get x cubed over 64. So it's the same basic form, but the extra x is distributed onto every single term. So where we'll pick up next time is looking at this example. 1 over 1 plus x squared, why that seems familiar is because if you integrate it, you get arctangent. And the idea we'll talk about is, if you have a series for a function, how can you get a series for its integral or its derivative? So if you have a series for 1 over 1 plus x squared, can you get a series for its integral arctangent? And the answer is yes, and you kind of do it like kind of the most natural way there is, but we'll talk about what that is. Okay. So those notes and this video is going to go up today. Also watch out for outline of what to expect for the next week and a half before we're totally done. If you have any questions, I can stick around, but if not,